So next up, we will have Joseph Poon and Chris Jeffrey. So Joseph is one of the co-creators of both Lightning and Plasma, and this is the first time that they are presenting publicly Warp, an algorithm, or what is it?
It's a
decentralized exchange, efficient decentralized exchange algorithm.
Yeah. Awesome. You got to look out. Hi, everyone. We're here to present an on-chain matching engine, and there's been no method in the blockchain to directly match buyers and sellers completely on-chain without capital-efficient liquidity pools with high price precision. And we needed this for an on-chain matching engine in order to make a decentralized cross-chain wrapping system for UTXO assets. That's not what we're presenting here today, but it's, I think the need in this space for a direct matching engine on-chain that supports things like the EVM to be critical in this space. And we think there's a broad applicability, and there are, in our construction has gas cost comparable with AMMs on the EVM. So I think it's important to go through what we're talking about through the historical narrative, because I think that'll inform what we're trying to solve, and also hopefully it gives some intuitions when we sort of present the solution, and maybe it's sort of like directionally as we explain the history, you can sort of see directionally where we're headed anyway. Now, there's in a normal centralized exchange, equities markets, whatever it may be, you're going to have these things called order books, and if you wanted to, let's say, buy 18 bags of apples, we all could see what should happen, right? You go to Wally, you fill his availability, and then you fill at 11 partially, right? That's easy to see for us, but there's actually not an easy algorithm to do this on-chain because of gas constraints. Because imagine if instead of a single order, sell order at $10, imagine if there's hundreds of these at hundreds of prices, like $10.01, $10.02. You're now doing read records on hundreds and hundreds of orders potentially at different prices, at different price levels, and at different price individually, all the way up to $11. It could be like hundreds or even thousands, right? And on the blockchain, you need constraints, capacity constraints. Otherwise, there's denial of service attacks. And that creates significant issues. So this gas limit problem is fundamental to what we're going to be looking at. So what are some early approaches? Ether Delta, they traded off price time priority. And price time priority means if you put in an order at a higher price, you get filled first. If you put in an order later than someone else, you're going to get filled later than them. Ether Delta was it's sort of like Craigslist or Facebook Marketplace. You throw the orders out there, it sort of goes, and then who knows what you're getting kind of thing in terms of who's getting it and in what order. And then there was a way to sort of abstract that complexity, that linear complexity away by running a central server. Now you are trusting the central server for matching, who knows what they're doing, but the general idea is that there's some centralized point of trust on the matching itself. Now you're not giving custody to them, but there is this process of that. And to this day, today, you sort of see this in the RFQ constructs. And what we think is very clever was the Gnosis Dutch auction. The Dutch auction construction was, there was a time decay. And if you fill it earlier, you pay a higher price, or a higher price gets set. The trade-off is, to do price discovery along something granular, it's probably going to take, maybe potentially days or weeks in order to do price discovery. But it is fully on-chain, and it is a way to do an auction system. So AMMs. Now, I'm sure most of us are familiar with AMMs, but I think what we want to point out here is that the kernel of AMMs is that you're providing a single price. By aggregating your orders together into a single liquidity provider, this problem that we had with these many different orders, well, you're just dealing with one guy, one record on chain. And you only need to fill one price. The trade-off, as we know, there's high capital requirements, you need to put in a lot of money, there's impermanent loss. Concentrated liquidity, adjusting the curve definitely helps significantly with that. But it doesn't eliminate the problem space. You still need to be supplying, $1,000 of X and $1,000 of Y to do these LP constructions. And auctions are very challenging, and auctions are necessary in order to do decentralized, fully decentralized oracles without, validators and trusted counterparties for crypto assets. And it'll continue to be useful and superior for certain applications, but we're strictly looking at, an order matching type of DEX problem here. What do we have today? So today, in terms of if you want to do, tight prices in DeFi, you have RFQs. You're essentially trusting some RFQ server to do this matching, and they're not really doing matching, they're more doing quotations, but it's the same general idea. They give you a price, you execute on it. If you choose to, you broadcast it on chain, people deliver prices to the RFQs. So there's some issues here with RFQs. It's a trusted intermediary. A sizable proportion of DeFi is now becoming RFQs. You give it a couple more years at the current trajectory, they're going to dominate, right? Like they just have the tightest spreads compared to other things on chain right now. Because they don't have to deal with these fee constructions and these other things, they're able to do it, right? And you have basically what amounts to be black box, centralized, opaque providers. And to give you a color on what we're talking about here, some RFQ providers in their docs, this is publicly disclosed, tell you that if you are supplying liquidity on RFQs, you can differentiate your users based on what website they're using. So if you go to an RFQ and get a quotation from website A, you can give them a different price than if they went to you on website B. So it's already self-selective and not an open market. But we think there's an opportunity here. I think the landscape has changed for on-chain matching. We now have smart contract L2s where we didn't before. Capacity has ballooned. There's so many L1s and L2s where we're only using maybe 1% of the available capacity, maybe less. And with more engineering, more work that everyone in this audience is participating in, or many of us, that I think capacity is going to increase even more with these roll-ups and ZK constructions and everything in the future. And I think we have sufficiently fast block times to start working on matching engines. And I think there's a lot of cool continued innovations ahead. So our contribution that we're presenting today is about a logarithmic matching engine. And it's important to find the problem of what we're looking at here, because I think when you see the problem, you can start to see where the solutions lie, right? The problem is fundamentally that you are filling many different prices, and that's a linear complexity problem. There could be thousands of orders with very, very small orders, because we're doing things on chain and we're dealing with an adversarial setting. Someone could fill, anywhere from, you want to fill from $10 to $11, there could be thousands of prices in there. So you could trade that off with precision, right? So you could say, okay, we've got an order book, we only have 10 different prices, maybe, and we only allow a certain amount of orders. Yeah, you could solve the problem that way, but that's not the experience that you have with traditional exchanges. That's not what people expect, and that's not a true matching engine at that point. So we constructed an EVM optimized radix tree data structure compatible with the EVM. The EVM has incredible constraints. 32 byte keys, 32 byte values. Fitting everything in 32 byte values is not easy, and fitting the data structure in which minimizes reads and writes is highly complex. Intermediate nodes, and here's the other insight, which is intermediate nodes, which JJ will be getting into soon, is they're going to contain both the child node's values and quantities. And that allows for true limit order books, auctions, and et cetera on chain, where all the executions happen inside the smart contract, all the matching happens inside the smart contract, and all the storage is in the smart contract. There are no validators, there's no cranks, it's happening on chain. The person that deployed the contract can walk away, shut off all their computers, it runs. It does its thing. We're talking about extremely high price precision. And this is the important point, because price precision is the problem that is being solved. You know, you can abstract it away with low precision. But if you want 1/10 of a basis points, that's a much bigger challenge, and that's sort of what people use in the Forex market. This is the standard. And we have a construction which is fully time-bound in the worst case at several 100,000 gas. It's very efficient, usually less than 200,000 gas. The worst case should never happen. We're talking about, potentially trillions of orders or billions of orders that persist over many years that never get filled. It should never happen. But in the average realistic case, we're looking at below 200,000 gas. It's comparable to AMMs. Most popular AMMs are around 150 to 200. Some do a little bit lower, but it's somewhere in that range. We have an implementation in both Solidity assembly and coming with C, which should be WASM capable.
Okay, so I'd like to quickly go over the problem. So the problem, as Joseph mentioned, is there's a lot of linear complexity going on in order books and matching engines. So problem, many orders can be placed at the same price, and one order may potentially fill an infinite number of orders or prices. And linear complexity in a decentralized system where n is unbounded is absolutely unacceptable. You can't do that on a blockchain. So the most well-known matching engines, at least the public ones, don't attempt to even address this problem. So our basic approach is to decouple matching and execution. And historically, these were considered the same thing. Matching and execution would happen at the same time. But by doing this, we can have synchronous matching and asynchronous execution. I'm going to explain what that means later. But this means that we can have log n matching. But first, I'm going to go over some of the traditional data structures that are usually used for order books and matching engines. So typically, the most traditional design that we could find, there's actually very little literature on this subject. A lot of these matching engines are trade secrets from centralized exchanges and whatnot. So, but the most traditional design is you use a self-balancing binary search tree or a radix tree. And the nodes are prices. And in each node, you have a linked list of orders. So like it has some decent properties, right? You have log n insertion, and you can optimize this and have O1 insertion if price already exists. You have O1 cancel, price lookup. But the big problem is like you have ON matching complexity. So this design first reached a wide audience as the result of now a frequently referenced blog post from 2011. It's like if you search Stack Overflow, if you search Google, like how do I write an order book, everybody references this blog post, which uses this design, which basically looks like this. So you have a tree, and each node in the tree is a price. And they point to within each node is a linked list of orders. A doubly linked list, right? So you get O1 insertion, O1 removal. But the problem is if you try to match, right, you have to iterate down this tree, iterate through these linked lists, go through every order and every price that the order satisfies. So you have the crazy complexity all over the place. And this is why this cannot be used on a decentralized system. So the other approach, which came around the same time, was the QuantCup approach. And around the same time, there was what was called the QuantCup.org contest, which was a contest to see who could write the fastest matching engine in C. And this was a minor improvement over the tree-based approach because it utilized a pre-allocated array of price points. So it's a little bit better than a tree because you get better caching properties, right? Because you're not chasing pointers all around this tree. You always have O1 insertion because you're always just going directly to a price bucket, which has a doubly linked list. But again, the problem is you have ON matching complexity. You have OM space complexity, where M is the number of prices. You have to pre-allocate this giant array. And there's a lot of limitations there. But it won the QuantCup.org contest, so this is another frequently cited design. And basically looks like this. So it's very similar, except that top row is an array. And each item there is a bucket in an array, which points to a linked list of orders. So it looks very similar to what we saw before. So our approach is a little bit different. I'm going to be showing you an example of our tree. In reality, we use a base 2 radix tree. But for simplicity's sake, I'm going to make it a base 10 tree so that's more understandable for everyone here. So the idea is you utilize a radix tree of prices and orders. So everything is the same thing, basically. So we have a decrementing, so we have a price. When you insert an order, you have a price. And we have a decrementing counter, which creates a decremented nonce. And you append that nonce to the price to create a path down the tree for insertion. And that's basically how you insert into this radix tree. That's what the path is. The idea for the decrementing nonce is you obviously want it to be higher for earlier orders to maintain price time priority, because you want earlier orders to go on the right side of the tree, because as you'll see, we're always going to be matching from the right. So like Joseph mentioned a little bit, so leaf nodes maintain 2 extra fields, quantity and value. Okay, so I'm going to need to define some things. So like quantity is so we have an ETH USD pair. Quantity is the left-hand side of the pair, or the base in quote, right? That's probably what a lot of people are familiar with. I'm going to say left-hand side, right-hand side, because I find it more understandable. So we have quantity, which is left-hand side of the pair, ETH, and price, which is the right-hand side of the pair, USD, and value, which is price times quantity, and the result is in USD. So internal nodes maintain some quantity and some value, where each of those fields are the sums of their children's respective values, right? So this tree basically has O log n for every operation, including matching. And execution is decoupled from matching. So execution is offloaded onto the traders themselves. And I'll maybe explain more of that later. But now I'm going to go through what an insertion into this tree looks like. Bear with me, because these slides can get a little bit complicated. Okay, so we have an ETH USD pair. We want to insert a bid for 1 ETH at $17.99. That's our root. So we have a counter, which decrements. We append it to the price, so we have 1799:9. That's our root. So our path is 1799:9. Our quantity is 1 ETH, and our value is 1799, because obviously 1 times 1799 is 1799. So what happens when we insert again? New bid comes in. Oh, also, sorry. Assume that the ask tree, this is a bid tree. Assume that the ask tree is empty. Because these trees, when these orders comes in, they sort of like eat away at the opposite tree. But right now we're assuming that the ask tree is completely empty, and there's only bids coming into the order book. So we insert another bid, 0.5 ETH at 1800. So there's a collision here, right? They both start with a 1 digit, so there's a split that happens. And now our root node has a prefix digit of 1. And the new bid that came in has a higher price. The nonce doesn't really matter right now, so it goes on the right. I'm sure you're all familiar with radix trees. The only big difference here is everything is getting summed up. All these quantities and values are getting summed up. And you can see the rightmost leaf has quantity of 0.5 ETH, value of $900, because the price is $1,800. So insert again, you know, same thing, counter decrements. This goes on the left, it's a low price. Insert again. So what we're doing is we're building a tree so we can match against it, right? So we insert again. Again, all the sums still apply. We go down the right side this time. It's a high price. Everything gets summed up to the root. We insert again. So this one's interesting, right? Because we go left, right, left. There's a split that happens, an internal node that's created, because now there's 2 orders at the same price, right? So if you look at the bottom left green node, which is a leaf, 1799:5 next to 1799:9, right? The :9, that nonce makes it go on the right side of the tree. Remember, we're always going to be matching from the right. So because the order to the right of the green leaf came in first, it gets a higher nonce, so it's going to get matched first, even though they're at the same price. And same thing here, right? So new node comes in, 2.5 ETH at 1802. And there's already an order at there's already a bid at 1802, but this one has a lower nonce, so it's going to get matched. It's going to get matched later, depending on what happens. So this is the final state of the tree, and now we're going to start inserting asks, and this is where the magic happens. This is where we're going to see the logarithmic behavior of our algorithm. Ask comes in for 4.2 ETH at $1,800. Now remember, we're always going to go right down this tree. So we go right, and then we hit the red node. And we notice that the red node, its path, not its price, its path, is higher than the asking price, right? So this entire subtree can satisfy this order. There may be 1 million orders, 1 million nodes underneath the red node, and we do not need to traverse them at all. All we need to do is delete that subtree and promote the left node. So we just technically matched. In this example, obviously, there's 2 orders there. There's 2 leaves. But pretend there were 1 million. We can match 1 million orders just by deleting that node. And then we tally up the value in an accumulator, the sum value, and then we sort of decrement the quantity that we're matching against. So this is what's going to happen. So the blue node gets promoted, and it takes that old internal node's place. We deleted the subtree in red, okay? So we didn't have to traverse either of the nodes under the red node. So once we promote this node, what happens is it's a partial fill. There's 0.3 ETH left over as a result of this order. Okay, so let's run through another ask again. And again, these slides take a while to grok, but I think you'll get it if you stick with me here. So another ask comes in. Again, we go right. This ask is for 1788 and a quantity of 4.55 ETH. We go right, we hit a leaf. We see that it's $1,800, so it's greater than the asking price, so it satisfies the ask. Again, we're going to promote the left node, so it looks like this. So we're promoting, blue node becomes the root, then we start going down the blue node again. Again, we're always going right. And this is what happens. So we go right again, we hit the right node, and we notice that the prefix digits 179 are greater than 178. So again, this entire subtree can just be deleted. And we can take the sum quantity and the sum value and tally them up. And then again, we promote the left node, and this is what we're left with. A partial fill, that's our root. That's the final state of the tree. Okay, so what's happening here? So the idea is that the seller's order is consuming as much as possible of the bid tree. And now the protocol knows exactly how much USD the seller gets and how much ETH they need to spend to get it. Any leftover ETH is going to go on the other side of the book. It's going to go into the ask tree as a resting order. So, and the ask tree is basically the inversion of the bid tree, right? It's the same exact behavior, it's just flipped. So now traders, like I said, there's asynchronous execution, right? So all we do is the matching. The traders actually need to execute their orders by claiming it. And the idea is they can go to claim their order, and you might be asking, well, how could they claim their order if it's deleted from the tree? And the idea is they have an ID for their order, which is the path down the tree, right? It's the price and the nonce and the side of the book, sort of. So what they can do is they can hit the contract and say, by the way, this contract basically only has 2 functions. It has order and cancel and claim are basically the same operation. So the idea is I want to claim my filled order. So what it does is it hits a separate storage record to make sure that order exists, and then it traverses down the tree. If the order is not present in the tree, that order is completely filled. If it is present in the tree, it's either partially filled or just not filled at all. It just like went on the book. and then they get whatever value was in there, and that would be a cancel, right? So claim and cancel are the exact same operation. So it's a very elegant system in that you only need 2 operations. You only need order and cancel. That's it. It's 2 operations. So like I said, our implementation on the EVM differs a lot from the examples I showed you. It's not base 10, it's base 2. Just because base 2 radix trees have a lot of nice properties. It's a lot easier to work with base 2 radix trees on the EVM because of all of the EVM's constraints. You know, you wouldn't want to use like some like base 16 radix tree, or just, and also we were writing this in Yule, which is how we got it so highly gas optimized. So the idea with our EVM implementation is that we have a 24-bit price, 40-bit nonce. So that gives you 2 to the 24 different prices, and that gives you about 1 trillion orders that can exist in one pair. It's so high, you'll probably never hit it. In our randomized benchmarks, the median gas usage for placing a limit order is around 120K. But if we exclude orders that fill immediately, and we only include orders which hit both sides of the book, the median gas usage jumps up to about 150K. Claims and cancels can be batched. So a cancel is normally around like, a claim or cancel is normally around like 70K gas. But if you batch them, and again, it depends on like the batch size. Like if obviously if you're batching like 100 orders, the median gas usage drops down to like 25K gas per order cancel. And the reason for this is like when you're getting like sort of like a slight gas refund by deleting stuff, and also like you're also hitting, you're repeatedly hitting like the same storage slots in the contract. So those are all hot. So it's like batching cancels can be very efficient. And to our knowledge, this is the first on-chain data structure which resolved a linear complexity problem, right? So this is the first truly logarithmic matching engine that can actually be used in a decentralized system, to our knowledge. So you might be wondering, you might be thinking, well, this is a radix tree. Eventually, it'll get fully saturated, right? And it'll have to do all these traversals just to get down all the price digits, and it'll have to do all this summing back up the tree when it inserts, and it'll have to reduce the sums when it matches, and so there's a possible optimization here that we're working on, and the idea is that the rightmost branch of the tree doesn't include its right node's sums. So the idea is that most often in an order book, people are placing orders near the top of the book, right? So that means they're always going to go on the right side of the tree. So if we exploit this fact, and we make it so that in the rightmost branch, the nodes don't include the sums of their right children, we can avoid all that summing during insertion and matching. And we believe, we don't have this optimization working quite yet, but we believe in the most typical case, the most typical orders could get around 100K gas usage, maybe even less than that. And Joseph, you take it from here.
Yeah. So like we are doing a high-level explanation. Like we said, like there's some changes with regards to how the radix tree is, like technically it's the 2 childs that are green, but it is what it is. So in terms of implications, we think it's useful for a wide range of DeFi applications, not just decentralized exchange. We need it as an auction scheme as well. An auction scheme is very interesting because like think about the normal DeFi, a common DeFi use case of, some liquidation of some underlying asset, and normally they use some oracle and then they sell it on the pricing mechanism in order to do that distribution. That oracle can get manipulated, as we saw with Mango. Instead, in order to reduce the potential for manipulation, what you could do is this thing that's getting liquidated, you throw it into an auction, people bid on it, people can arbitrage it out with other exchanges, and that's a lot harder to manipulate because if you put in a low price, someone's going to put in a higher price, right? Like it's very hard to do right now to do an auction scheme of like a large asset with many different bidders with small amounts because functionally you need an order book. You need an on-chain order book. And I think it can provide, as a result, an alternative to the composability design pattern. And composability, oftentimes, you're hitting other contracts in order to fulfill whatever you're looking to do. And maybe you could just auction whatever it is that you need, and that you leave it up to market makers to do this composability functionality. AMMs inherently, due to impermanent loss, have some percentage costs. And they need to account for impermanent loss. We think that market makers basically are capturing the bid-ask spread under this construction, and maybe that can tighten the competitiveness in this space with regards to centralized exchanges, RFQs, and things like that. So what are the opportunities here? I think it brings about when you can do an on-chain order book. I think we can do a new round of L2 innovation where, if you think about it, with a lot of these roll-up constructions, the primary cost being borne is the cost of the data availability on the L1. So you take a transaction, you broadcast the call data on L1, or it gets bucketed together and broadcasted on L1. And that would likely require, but maybe instead, you flash the orders on the L2, and it's only when it matches, when an order gets filled or partially filled, that you even need to prove data availability. Because if an order gets issued and canceled on an L2, why do you really need to prove anything? Like, no money has really changed hands. And that allows you to really reach scale where you can issue maybe like an incredible amount of orders per second, and a certain percentage gets filled, and those get committed on L1s. Now, this probably requires some opcodes and changes on the L2s, but it's theoretically possible, right? I think you could, because you could do commit reveal schemes, you could commit to something and then say, okay, I actually did the order at this price and do it at a later date. I think it becomes interesting and necessary for these types of things. What I think is really promising with this is because we have bounded complexity. Specifically, it's a tree that has a depth of 64. All the other order matching algorithms out there that are published have linear complexity, i.e. infinite, basically, complexity, where, near infinite, where at each price you can fill each possible price. And that's a lot of possible different prices. How are you gonna unroll that loop, right? With this, you could have a 64 deep loop, you unroll it, and then you may be able to do interesting things like ZK constructions off of this to build a true central limit order book with a ZK construction. So I think, when we think about we're building, if we have an on-chain order book, if us as a community, if we have this as an algorithm, we could just broadcast an order. It hits a full node that either you run, at home or, in some data center, and you're doing the execution on your computer, or a computer that you authorize. You're doing the matching on your computer. You're doing all the data is on your computer. All the data gets broadcast everywhere together. That's very different than centralized exchanges, equities, like the New York Stock Exchange, NASDAQ. You're hitting some server. And this is a construction where you have everybody computing everything together. And I think that gives us an opportunity to explore new avenues and gives us the ability possibly to see, to show traditional markets what the opportunities are. So we have an EVM Solidity Assembly version, also known as Yule. We're releasing around mid to late September 2023 in order to maybe see if the optimization is possible and also do some code review. Yeah, we're definitely looking for code and technical comment on this. Yeah, and we'd be honored to have your review on this. Yeah, thank you so much.
Thank you.
I have a couple questions if people want to line up at that mic and that mic over there. So I think it's very impressive what you've done to reduce the cost of execution, but if you still have the cost of placing orders and canceling orders and claiming orders linear, the whole system is still linear in the linear gas costs and the number of orders, right?
Yes. So the problem is not necessarily the gas costs in terms of the fact that, well, there are concerns with regards to that, but the order issuance in order to insert an order is bounded because there is that depth. So functionally, like if it costs some N amount of gas, let's say it's like 120K in order to do an insert, that's not infinity, right? The problem is principally with matching, which is infinity.
But it is still proportional to the number of orders that are being placed.
Oh, definitely.
Yeah,
We don't have a
execution.
magic system where you can insert an order.
Matching is log n.
So you can't insert 1 billion orders and it all fits in a block. That's not possible. Yeah.
On an AMM, because orders automatically flip when they're crossed, and because you can place orders across a whole range, you don't have costs that are proportional to either the number of prices you're placing orders at or the number of times you get crossed. So there's still sort of a different complexity class in that.
Yes, yes. But we're presuming that the cost of insertion is going to be comparable. And additionally, there is this question of, okay, if you have a lot of insertions and cancels on this book, what does that mean? And that's a matter of the spread, right? But in addition, we think with L2s and these new constructions, you could perhaps issue an order on L2, do a cancellation, and it doesn't really bear any real world, well, not significant real world costs.
First of all, thank you very much, guys. Brilliant presentation. I have good news, I have bad news. Good news, I can confirm it does work in practice in the real exchange. The bad news, we run the similar model for about a year now. At ZKX, we separate the execution from batching and matching. The only massive issue in the real exchange is when you have mass automated trading strategies, the cost of order placement goes by order of magnitude. So in your optimization, you've proposed optimization within the one network. What we've seen so far, that in order to keep the cost down for the automated trading strategies, you have to separate execution and keep it, let's say, in our case, it's starting at L2, while matching and batching happens at L3. So maybe consider separation and isolation not in the way of just batching and matching and then execution, but in a different network as well. Because for us, it was the biggest issue with, we only charge fees for the orders that have been matched, but the mass value of orders are withdrawn before they're matched by the automated strategies. So for us, the answer was to just separate between L2 and L3. Maybe,
yeah, I think the separation when it comes to L2 is relevant. What we're specifically talking about is a radix tree construction where the sum value is included.
Right, we're not claiming to have invented separating out matching and execution. Like, we are aware that that has been a thing, like that's a basic, and that's a basic pattern in a lot of smart contracts. That whole claim pattern, right? You don't want the contract just automatically like sending things out. So, I mean.
And there is a follow-up for that. In your randomized strategy, you've tested 20,000 transactions. In our case, for some reason, which we're still trying to explore, when it goes about 150,000, it goes exponentially in terms of the cost.
That's what we're solving. That's
Okay.
specifically
That's the optimization we discussed? Yes.
Like we didn't put our contribution today as the separation of claims. This UTXO pattern of an output that you claim at a later time is a pattern that occurs, is a logical pattern for this type of stuff, and definitely we do believe other people have implemented that. It's specifically the radix construct, the keeping everything within 32 bytes, and this sum value that makes it logarithmic.
The matching algorithm.
But it's definitely working, so congrats.
Thank you.
Thank you.
Thank you.
One more question?
So I believe you developed this design with the sort of EVM model where all the computation is going on chain and all the traversals to find the match happen on chain. Other chains, they allow you to do all of that kind of computation to navigate through the tree and stuff in off-chain code without incurring any cost.
Right.
But then for the on-chain validators, you need to prove that wherever you ended up and whatever paths you kind of collected are the valid ones, and you're not kind of, you're not in the wrong part of the tree or whatever, right? How would your design change if you kind of were to lift your constraints in this way, right?
So we have these aggressive constraints because when you offload it to a centralized server, they could do things like censorship. They could preferentially execute with their friends.
Oh, sorry, I wasn't clear. What I meant was, I don't mean that you are trusting someone to do the navigation. What I mean is that the validators, all they care about is that, like in the UTXO model, right? You can say, I'm consuming this UTXO, that UTXO, that UTXO, which is great. It limits you from being able to traverse the entire global data structure because you're limited in the amount of information that you can provide to the transaction, right? But if your data structures in the UTXO model are constructed in a way where you can prove them, oh, I'm actually in the right side of the tree right now, and I'm consuming from it, right? Then you can, all you have to do is show that. You don't have to traverse the whole thing in the on-chain code, right? So how would your design change if you have the ability to just prove that you're in a particular side of your tree without having to traverse the tree in the on-chain kind of execution environment?
So we have this constraint for a reason. We have this constraint because you can, on that off-chain thing, manipulate things in terms of who gets into the tree itself. But if you relaxed it, obviously, you don't have this problem of, block size constraints. So,
Right.
the recommendation would be use more traditional methods.
Okay.
All right. Thanks very much, Joseph and JJ.
Thank you so much.
Thank you.
This, now coming to the first break. Pick up again in 20 minutes.